Welcome to this hands-on video tutorial on setting up and running the UFS Short-Range Weather Application or SRW app cloned from the UFS GitHub repository. In this session, we'll walk you through the setup process and then dive into a detailed exploration of the output data and image files generated by your forecast experiment. I'm Priya Pillai, a member of the Epic user support team. This is the second video in our SRW tutorial series. And in our first video, we demonstrated how to build and run the UFS SRW app version 3 using its container image. By the end of this tutorial, you will learn how to generate output image files from your SRW app experiment, use basic data processing utilities to inspect and interpret netcdf and grip2 outputs, and apply image visualization tools to explore your forecast results with confidence. In this tutorial, we'll guide you through three key sections, which include cloning and building the SRW app version 3 from the Epic GitHub repository, followed by model configuration setup, outputs, and plot walkthrough. The last two sections apply to both containerized and non-containerized setups. In addition to the Intel compiler, MPI, and the Recorder Workflow Manager prerequisites, users who are not working on the Epic Level 1 platform will need to install the prerequisite software stack using the SPAC stack prior to building the SRW app on a new machine. SPAC stack is a repository that provides a SPAC-based method for building the software stack. For installation instructions, please refer to the official SPAC stack documentation. You will also find detailed guidance to install the prerequisite software stack in section 2.1.1 of the SRW app users guide. And if you have questions or need support, post it on the UFS community discussions hosted on the Epic community portal at epic.nova.gov. In this demo, we'll run an out-of-the-box weather forecast for June 15 to 16, 2019. The forecast uses predefined 25 kilometer continental US grid known as the RRFS_CONUS_25 kilometer. It is configured with the Global Forecast System version 16 physics suite. For model initialization, we use v3 based GFS external model data. That means your initial and boundary condition files are from this model data. Now let's copy the input data or make sure that the input data is already copied and made available to run this experiment. Once you are logged into your HPC system, use the cd command to move into the directory where you would like to copy the input data for your test run. cd path to the input data. Under this desired location, create a new directory called input data using the makedir command. Then move into that directory. For that, use cd command. Now download the required data tarballs using the wget command. Once we copy the input data for our test case, we'll now create a clean workspace. This ensures that our files are organized and easy to reference later. Use the cd command to navigate to your desired location under which you are going to create a new working directory. I'm going to use cd command to navigate to work2, under which I'm going to create a new directory called SRW tutorial 2 using the makedir command. You can give any name of your choice. Export the newly created directory name with its entire path to an environment variable called work using the export command. After this, change your working directory to the newly created directory using the cd command. Use ls-lrt command to list the content of this newly created directory. You can see no files there as we just created it. We'll now use module load contrib command to load the UFS maintained software package contrib into lmod availability environment. That means it will make the module files discoverable if you are using commands like module show, etc. Now use the command module show contrib to inspect what is included, and you can see there are module files, and list the module files using the ls command we see that it includes a module file named Noah Tools. Now use the command module load Noah Tools to use this software package. The module show Noah Tools command reveals its configuration, which include saccount param script. Run the saccount params for inspecting usage metrics like CPU hours, disk usage, etc. This is critical for job submission and resource tracking. Let's begin cloning the repository using the git clone -b command, where -b followed by the branch name, release / public -version 3.0.0 ensure that we are cloning the public release version 3 branch and it is the most recent release version. Run the git clone -b command with the GitHub repository name and the branch name. Use ls-lrt command to see the files and directories, and we can see a newly created UFS SRW App directory once the clone is complete. Now we'll set an environment variable named SRW to this UFS SRW App directory to simplify the path references later. For that, use the export command. For example, here export SRW equal to $var -UFS -SRW -app, where $work is the environment variable you already set for your workspace path. Now let's move into the UFS -SRW -app directory using the cd command. To see which branch is active in this cloned repository, run the command git status -b and make sure the public release version 3 is the active branch. If you would like, you can run the git branch -a command to list all the available branches. The active branch is highlighted in a different color or is marked with an asterisk. The SRW app relies on external components. Therefore, we must run the checkout external script to collect the individual components of the SRW application from their respective GitHub repositories. For that, run the command ls-lrt on manage_externals directory. And you can see many files here, and in that we'll see the checkout_externals file or script. So run that script using the command /manage_externals /checkout_externals. Let's build the application, and please remember I'm running this test case on tier 1 platform Hercules. If you run the command uname-n at the terminal, you can see your platform name. Use this platform name as an option with this build command. To compile the source code and build the SRW application specific to Hercules platform, run the command as follows: /devbuild.sh -p equals Hercules. It launches the dev build script specific to Hercules platform. Now use module use command to load the module files under this directory. Module use $SRW /module files adds the SRW app module files directory to the module search path. Following this, use the command module load workflow_Hercules to load the predefined module file for Hercules. Let's now activate conda environment using the command conda activate SRW_app. In this step, first we need to update an input file to enable composite reflectivity, which is an important parameter in forecasting severe weather. To enable composite reflectivity plots for FV3 GFS V16 suite, we need to update fv3.input.yaml file. Navigate to the parm directory using the cd command. Here, using the vi editor, open the fv3.input.yaml file. Once you open the file using the vi editor, the default mode is command mode. Press escape key to make sure that it is still in the command mode. Once you are in the command mode, press :508 to navigate to line number 508. Now press the key I to move to insert mode, where you can actually type and edit the text. Here the field is LRadar, which is set to null, and update it to true. only use spaces when making entries in YAML file. Once this is updated, return to command mode by pressing escape key, save and exit the file using the command :wq, press enter. Now we are in the parm directory. Come out of this directory using the cd space _ command and navigate to ush directory using the cd ush command. List the available model configuration file template using ls space config star.yaml, which will list all the files, begins with config and ends with .yaml extension. As a next step, we'll copy the community YAML file to config.yaml file. For that, I'm going to copy the config.community.yaml into config.yaml. Open the file using the VI editor. I'm now updating the config.yaml specific to this experiment setup and platform I'm using. Users are advised to refer the SRW tutorial 1 for detailed information on how to update the config.yaml file. I'm updating machine to Hercules, which is the machine that I'm using, and you already know the name of your machine, so update this field here or run a uname space -n command to know the platform. Now update the account field in which I'm going to update it to Epic. This is the group I belong to. If you want to know the group you belong to, run the groups command in your Linux terminal. Under the workflow key, you need to set the cron job relaunch parameters. For that, use the cron to relaunch variable to true and set cron relaunch interval minutes to 3 here. That means every 3 minutes, the recorder workflow will relaunch the job so that user does not need to relaunch the job manually. Now come to the external initial condition files, which is task get underscore extern underscore ICS. Here we are going to set use user staged external files to true. That means the user will be providing the path to the input ICS file. Now we are going to update the external LBCS key. And here also the external LBCS key is set to true because the user is providing the LBCS files here. At the beginning of the tutorial, I showed you how to get the input file using the wget command. If you need more help on how to copy the input data, you can refer to tutorial 1. For this, we already know where we have copied the input file. Here, update the path to the input ICS and the LBCS file. We have already covered the details in the tutorial 1 except for the plotting. Under task underscore plot underscore all vars, we are adding 2 new keys for plot forecast increment and plot forecast start time. For plotting, I am setting the plot forecast increment to 3 and plot forecast start to 1. This means I'll be getting the plots every third forecast hour starting from the forecast hour 1. You can set the forecast increment to your desired value starting from 1. Setting the plotting domain to regional. We already know that SRW App produces regional forecast, so this is ideal to set it to regional. Another important step in producing plots or PNG files is under recorder task key, under the task group, we need to add the following YAML file list. These file lists are parm/workflow/prep.yaml, under the same directory coldstart.yaml, post.yaml, and plot.yaml. And they include followed by pipe symbol tells that append all these YAMLs so that the task group will include the information from all these YAMLs. After making these updates, now it is time to save and exit the config.yaml file. Use :wq command and press enter key to save and exit the config file. And now it is time to generate the recorder workflow. This workflow orchestrates the model run and the post-processing and plotting tasks. For that, we need to run the Python script generate _f v3 lam_workflow.py. We have to submit /generate underscore v3 lam underscore workflow.py. After you run this Python script, you can see the terminal output. A new experiment directory is created under which there is a test community directory is also created. And it is now time to navigate to this directory. Use the cd command to navigate to the test community directory. Run the list command, that is ls-lrt, and XML and database files are also got created. XML file has .xml extension. You can see database file which has .db extension. These are the files Recorder uses to manage the task. Recorder stat command lets us monitor the progress and diagnose issues. Under the test community directory, run the following command: recorder stat -w fv3 lam underscore workflow.xml -d fv3 lam underscore workflow.db -v space 10. Running this command with -v10 option outputs the very detailed information about each task as you see here. If you give the entire path of these files, you can run the recorder stat command from any directory. Monitor the status of each of these tasks, and you can see that the status of different tasks shows as succeeded, submitted, or queued. And these tasks include make grid, get external ICS and LBCS files, make ICS and LBCS files, run the forecast, and create image files. And continue monitoring the state of each of these tasks. At the end of the run, all these tasks should show as succeeded. It is now time to explore the SRW app outputs generated by this experiment. Before that, we would like to make sure that you know how to switch between login node and compute node. On a cluster-based SPC system, it is extremely important because login nodes are meant for lightweight tasks like editing files, compiling code, submitting the job to the workflow, or monitoring the task, etc. When we are using data manipulation tools on large data sets, it becomes computationally heavy, and therefore it is highly recommended to switch to the compute node. If you want to know whether you are in a login node or compute node, you can run the command hostname. If it lists your system name with login information, then you are in the login node. Switch to compute node, you need to run the command srun-n space 1 -x11 -pty space bash. That will take you to the compute node. After you enter the compute node, if you run the hostname command, you can see your platform or system name is listed with a number, and that makes sure that it is in the compute node. If you list the modules available, you can see no modules are listed because modules you have already loaded in the login node. It is for the login node, and for the compute node, you have to load them separately. Once the recorder command shows all the tasks are successful, it is now time to explore the SRW app outputs generated by this experiment. And we are now in the test community directory. Now run a list command on the grid directory. Here you can see there are many files, and these grid files defines the horizontal grid structure, which include the lat/lon information, etc. It is generated during the make grid command. Let's explore the orography directory, which is named as orog here, and it contains terrain height related data for the model grid. In the surface climatology directory, which is sfc_climo, you can see there are many files which include surface climatology, vegetation type, albedo, soil type, etc. The fix LAM directory contains symbolic links to the input files that is required for the limited area model runs. It is created during the model setup. And finally, one of the most important directory, which is the log file directory, which is named as log here. And these log files are got generated during each task of the model run. If you see the name of that, it is familiar to you because it is the name of the task you noticed when you run the recorder stat command. For each of these tasks, log files got generated. For example, let's open the log file for the recorder workflow, and you can see information about each task run as part of this workflow. The time when each task was submitted, information about model's execution, capturing runtime messages, diagnostics, and errors, etc. Therefore, when something fails, these log files are the first resort to see where it failed. Now let's explore the main output directory, which is 2019-06-15-18. There are physics files for each forecast hour starting from forecast 0 to 12, and it stores output from the physics parameterization schemes and contains surface fluxes, sensible latent heat, cloud properties, radiation fluxes, and precipitation, etc. There are dynamics files as well for each forecast hours, and it contains prognostic variables such as zonal and meridional wind components. That means zonal means U wind and meridional winds means V wind, and temperature, pressure, geopotential height, etc. from the model's dynamic core. And there is a restart directory. Let's list the content of the restart directory. You can see there are many files here. This restart file is a snapshot of the model state at a specific time. Now let's navigate to the post PRD directory. This directory contains the final output from this experiment or from the model simulation. When we listed the files in this directory, you notice there are many files with the .grip2 extension and .png extension. Files with grip2 extension are called gridded binary version 2 files, and .png is the image files. We notice that there are many netcdf files, and we want to explore these files. For that, let's run the command module avail netcdf, and you can see there are many netcdf modules available on the system. Let's now load the netcdf-c module. Here, you can run an nc dump -h command. It will list the header of that netcdf file. It is the most important information that is in the netcdf file. Actually, the header contains information about the content of that file, which include dimension of the file, variables contained in that file, variable long names, variable unit, etc. So if the terminal output is going to be long, always use the command with a pipe symbol followed by more option so that you can see the terminal output one page at a time. To see the content of a gridded file, you need to load the module wgrip2. For that, try or run a module avail command. And now let's load the module. Once it is loaded, you can explore the grip2 files. Let's see what is inside a grip2 file. Now let's run wgrip2 command on a grip2 file. For example, let's explore what is inside this grip2 file. Use wgrip2 followed by the grip2 file name, and then you'll see many outputs, and with users who are not familiar with this kind of file format, it is hard to interpret what is there. One easy method is convert it into a netcdf file, wgrip2 followed by grip2 file name, and give the option -netcdf, and then you can give any name for the output. So let's explore what is inside the newly created netcdf file. Use the command nc dump -h srw_try.nc, and you can see many variables. They are orderly listed here. It is more easy to read for a user who are unfamiliar with the grip2 file. These are the image files, and there are different image files for sea level pressure, 2 meter temperature, 2 meter dew point temperature, 10 meter wind, surface cape, composite reflectivity, etc. Remember how we set the composite reflectivity plotting during model configuration setup. Now let's explore what is inside this PNG file. For that, try a display command on any PNG file. It says command not found because we have not loaded the module to see the image. So let's explore what modules are available using a module avail image command. There are two image magic modules, and using the module load command, load the image magic module. And after it is loaded, run the display command on any netcdf file. Here I'm going to run it on composite reflectivity. It's a regional plot because we generated the regional plot. So let's display that, and you can see the composite reflectivity is displayed here. So this plot shows the high reflectivity region, which is obviously the cloud region here. So now let's explore the 2-meter regional file. Once you open that, you can see it is the 2-meter temperature, and the unit is also given. And this is for the forecast hour 8. You can see high temperature regions are shown in orange color. Low temperature regions are yellow or green color. Now let's explore QPF. QPF is the 12-hour accumulated precipitation in inches, and you can see the color bar as well. Same way, explore all these PNG files and try to familiarize with the output. ncomp command is a powerful command which we can use to compare two netcdf files. ncomp stands for netcdf compare and is a command line utility to compare the netcdf files either bitwise or with a user-defined tolerance value. Before running this command, we need to make sure that it is loaded. Run the command module avail ncomp, and you can see it is available. So run the command module load ncomp so that it is loaded now. Format to use the command is ncomp netcdf file 1 followed by netcdf file 2. You can also give more options in this command. ncomp-d followed by netcdf file 1 followed by netcdf file 2. Compare the data outputs in these two files. ncomp command show no output if the files are identical. But if the files are different, for example, here I am giving a different file as netcdf file 2, and you can see some outputs printed on the screen. There is not much information. For a detailed information of this comparison, you can run the command with more options. Here I am running it with ncomp-d fqs, and you can see that the difference is given with more details, and a statistics of the difference is given, which include sum, etc. Here you can explore more options using the command ncomp-help. For additional details, you may refer the website provided here. This marks the end of the tutorial, and thank you for watching. You may reach out to us at support.epic@noaa.gov. If you have questions or need additional support, please post it on the UFS GitHub discussion or Q&A forums hosted on the Epic community portal.